We said it's important to carefully design your experiment, so let's look at experimental design. By the end of this lecture, you should know different types of experiments and know that some of these types are more efficient than others at proving causation from the data. Maybe the most well-known type of experiments are the randomized comparative experiments, and their name was well chosen. When you have a randomized comparative experiment, your subjects are randomly allocated to one or several treatments, so that's the random part, and the responses are compared across treatment group. So we compare, and because we impose a treatment, it is an experiment. We've seen an example of that in the last section when we randomly allocated students to different groups of ad exposure. When in an experiment you have two different groups of people, one being the control group and the other one being the treatment group, the difference in responses you have between the two groups could come from the treatment, of course, but they could come from pretty big differences between the individuals in the group. It is sometimes possible to avoid this problem by using what we called matched paired experiments. So let's look at example. Let's say you want to know if some drug works. So what you could do is take pairs of twins. And for example, for the first pair of twins, you give the treatment to one of the twins in that pair, and you give the placebo to the other one. And then you do that for several pairs of twins. And now if you want to compare what happens in the placebo group and in the treatment group, you really have control for the difference in genetics. Another example we could have, if you want to know if some diet works, if you use complete randomization, what you would tend to do is take a group of people which are the control group who don't do the diet, and then have another group of people who do the diet. But there's actually a better way. Instead of having these two independent groups, what you could do is look at people before the diet and after the diet and see how the diet has changed things. And because it's the same person, it controls for variation between individuals. When we do things like that, and in fact, so in that case, we have two groups, the before and the after group. There's a pairing between these groups, of course. If you're looking at one person before the treatment and that same person after the treatment, then of course these two observations are paired because they're about the same individual. If you look at your treatment for some drug in twins, then the twin in the same pair would be matched. You know, what happens for that twin with the placebo and what happens to that twin in the same pair with the treatment. So there's a natural pairing between the two groups. And when it's like that, we call this a matched pair design. And these produce a much more precise result than complete randomization because we are controlling for variations in response across pairs. Example, a study was conducted on students to see if smartphones use as an effect on driving. I bet it has. So a driving simulator was used to test students' driving skills by measuring the response time. So the goal is to know if talking on the smartphone affects your driving skill by slowing reaction time. So that's the research question. And below, we consider two possible experiments which we could design to answer this question. First experiment. You'll start with 40 students. 20 of them are randomly assigned to a smartphone treatment, which means they use the simulator while talking on their phone. And the other 20 students use the simulator, but they're not talking on the phone. And then we measure their reaction time. Experiment number 2. We work with 20 students only, and we ask them to use the driving simulator twice, once with their smartphone and once without. And we make sure the order of these two treatments is randomized. That's important actually because maybe people could get better because they're practicing. These two experiments could answer the research question. So now we have a question for you. So step 1, what is the name of each of these two experiments? So I'll let you think and write it down. Which experiment do you think provides better information for answering the research question? These are questions you will be asking yourself when you actually want to answer a research question, maybe because you're writing a memoir or want to produce some research. And then you need to justify your answer. Why is that the case? So please pause the video and write this down. The name of the two experiments, the one where we had two independent groups, that's called a randomized comparative experiment. And in the second one, it was the same student driving twice, with and without the cell phone. So a student is matched with itself, is paired with itself. So that one was a matched pair design experiment. Which one will be better, will give more information to answer the question? It's the second one. Yeah, you can imagine someone who would be really clumsy and not good at driving. And so you could see if driving in that case affects them. Whereas if you had this person who's was a really slow reaction time, not a good driver, and you put them in one of the groups but not both, then that could affect the results of the experiment. So the reason why it's better, in other words, is if it's the same student using the simulator both times, this controls for difference between individuals, right? We don't have the same driving skills initially. And one more question for you. Why do you think we've been using a simulator? And that's going to help you design your experiment too. And the answer is ethics, right? I mean, we expect that people are not going to driving as well if they use their cell phone, and we don't want to kill people just because we'd like to collect data. Let's explain what a randomized block design experiment is in the context of an example. So let's say a pharmaceutical firm has developed a new drug and wants to know if it's effective. So right now, that's what they're interested in. Does it work? It turns out that men and women could react differently to some type of medical treatment. So what you may want to do is look at men and women separately. So a block is a group of subjects known before the experiment to be similar in some way that might affect their response to treatment. In a randomized block design, the random assignment of subject to treatment is carried out separately within each block. What that means in that case is you would look at men and women separately to define a control group within the block of men and to have a treatment group within the block of men, and then you would compare those two. What that means is you know that there are several factors who could explain what you see in the experiment, and you're trying to block off to make equal the factors which are not the ones you're interested in at this point, in that case, gender. So the variations come only from the factor of interest, which is in that case, the treatment you apply. This is not totally new. We've looked at matched pair design experiment and they work along the same line. So let's say we come back to this example of testing if a drug works. You could have a small block made of two twins. And if you compare what happens within this block, it means that you are ensuring that the genetics is the same within this block. So similar in some way that might affect the response to the treatment. And that way, you know that what varies is the factor of interest, in that case, whether they receive the new treatment or not. A word of caution about experiments. You need to choose an appropriate control. The only thing that should vary across treatment is the factor of interest. And you will need to use a placebo to compare what would have happened in the absence of any medicine, for example. So you have something to compare to. And beware of bias. If the person who administered the treatment knows what's being applied, it may even subconsciously bias the way they work with the subject. Let's imagine the case where you want to test a really powerful drug, and let's say one of the treatments is the placebo. The second treatment would be a low dose of the medicine, and the third one would be a high dose. If the doctor knows which one they're giving to patient, they may present it to them a little bit differently. For example, they may explain really well in case something goes wrong when they give the high dose. And then when they give the placebo, it could be, oh yeah, take this twice per day. You know, nothing can really go wrong. So their body language, the tone they indicate, the time they spend could be an indication for the patients of whether they are receiving the real one or not. And also if they see that the doctor is not concerned at all, they will think, okay, that's not a very strong thing. So that could influence the results. So ideally, we like double-blind experiments. So blind to the subject, they don't know what they are receiving, but blind also to the person giving the treatment. So one way to do this is it's decided by someone, let's say, which groups receive what. They write this in an envelope and then they seal the envelope and hide it somewhere. And then they just tell to the people administering the treatment, your treatment 1, treatment 2, treatment 3, and they have no idea which one is which. More cautions about experiment. You need to replicate the entire treatment. So that means if you want to be sure something works, it wasn't just something that appeared by chance this one time you did it or due to a mistake. You need to repeat the entire treatment independently for different subjects. You don't want to be using the same machines in the same room with the same people, because maybe if there was a bias the first time, it could be by accident repeated the second time. So when it's something very controversial, you may have read in the newspaper, then another lab will actually try to replicate the treatment in a different place with different people. So different subject, but also different people administering the treatments. So it's not the same to apply in one go a treatment to 1,000 subjects or to do it to 10 groups of 100 people each when it will be done separately. And then you need to try to make your experiment realistic. And if you think of the one where we inject some nicotine to guinea pigs when they're pregnant to see what happens, well, it mostly shows that nicotine is detrimental to guinea pigs. So, I mean, they're mammals, we're mammals, but it's not the same as doing the experiment on humans. I mean, in that case, maybe it was hard. So try to have something as close as possible to a real situation when there is a problem you want to solve. So now that you know everything that could go wrong in an experiment, let's look at an example. So we want to know the effect of marijuana, and let's look at a study. So a study of the effects of marijuana recruited 20 young men who have been using marijuana in the past. Some were randomly allocated to smoke marijuana while others were given placebo cigarettes daily. After a week, their ability to concentrate was measured. It's not a fantastic experiment for a number of reasons, and I'd like you to think of that, and I'm not going to give any hints because there's an exercise like that in the tutorial, and it's really great if you can discuss it as a group, much more interesting than listening to me giving you